So in this lecture, I'll be dealing with the topic of algebra of scalar, vector and tensor functions. Now, in fluid mechanics, you encounter all three types of fields or functions. So this is very important for us to be aware of the mathematical sort of tools that we need to be familiar with dealing with these quantities. So the learning objectives of this lecture are how to represent vectors, tensors in general coordinate systems using a specific notation by the name of indicial notation. So this is something that we actually we know this, but we haven't been trained in a manner to recognize this earlier, and the main emphasis is on general coordinate system, so not necessarily confined to or attached to a Cartesian coordinate system as is usually the case. So we will learn to represent vectors, tensors first in general coordinate systems using indicial notation, and then the next objective is how to handle various algebraic operations. Now, what are the algebraic operations? Normally what you have are addition, subtraction, and the dot and the cross products and things like that. Okay, so these are the algebraic operations in general. So how to handle these algebraic operations involving of course vectors and tensors. For scalars, you don't have any dot or cross products and things like that. You are only you only have the addition, subtraction operators. So that is very straightforward. For the sake of completeness, it has been mentioned here. So, and since most of the time we deal with orthogonal coordinate systems, Cartesian, cylindrical, these are all orthogonal coordinate systems, meaning that at each point described by these coordinate systems, the unit vectors are mutually perpendicular. So how to handle algebraic operations in such coordinate systems? Okay, now we move on to the formally beginning the algebra and calculus. So in fluid mechanics, we deal with three types of all the three types of physical quantities: scalars, vectors and tensors. Examples are like density, temperature, kinetic energy, and even pressure. We will show that actually pressure is not really a scalar, but it behaves as one. So it can be put into the category of scalars because of its behavior and mathematical treatment. And then vectors, of course, velocity, field and velocity vector is the most important thing in fluid flows. Acceleration of particles, forces, vorticity that we have just learned. What is vorticity in local rotation rates? Portion of my lectures. And then you also deal with tensors in fluid mechanics. We have already seen the in a three-dimensional flow field we have six sort of characteristic local deformation rates, 3 longitudinal and 3 shear, that we use to characterize the strain rate at a point. So we will show later on that this quantity is a tensor, and of course we are going to shortly handle surface forces acting on a fluid particle. So we will be using the idea of stress at a point there. Stress at a point you have been learning in earlier course in fluid mechanics as well as solid mechanics. So I will assume that stress at a point is a well known and established concept at this point. So just to have a quick look at the differences from mathematical point of view in these three quantities. So you can see that scalars, as we all know, they have got a magnitude only. So you just assign a sort of a real number to represent that magnitude. And for vectors, you have two things associated, some magnitude and a direction of this quantity. And if we extend this idea further, tensors of rank 2, they have a magnitude, three things associated with a tensor at any point in the flow domain. It has a magnitude, but it has information of two directions. So I've written here as direction 1 and direction 2. So there are inherent three things associated with a tensor of rank 2. It has a magnitude and two directions. Now at this point it is sufficient to just understand this much only. Later on, when we examine the stress and strain rate tensors and all, we will get to understand, depending on the physical quantity, the meaning of these two directions. Okay, at this moment it suffices to understand that vector has a magnitude and a direction, two things, and tensors have got magnitude and two directions associated with them. That means if you want to represent them, you will have to find a way of representing the three quantities. Okay, now we move on to some notations that we will follow. In general, for this the lectures on mathematics that I am going to take, the present one and the upcoming next lecture, both will be on algebra and calculus of scalar, vector and tensor functions. So I'll be following this notation. I'll represent a scalar function or a field as simply phi r t. R here means the position vector of any point in space and time. So because I am not restricting to only Cartesian coordinate systems, in general I am considering any kind of a coordinate system. So that's why I just write R and not x, y, z and t. Okay, vector field, again a vector, some vector a, and it's distributed in space and time. Similarly, a tensor field. So tensors, I will second rank tensors, I will just symbolically write them as t and double horizontal lines on the top. So two lines indicate that it's a tensor of second rank, right? Now we will focus on how we represent them in any coordinate system, the vectors and tensors. Now as you all know, vectors, you are familiar. If you start using the unit vectors in your coordinate system, and in 3 dimensions you can write the unit vectors along coordinate directions as let's say, for the sake of symbolic reference, we call them as E1 cap, E2 cap, E3 cap, and not necessarily I, J, K caps, because they are just unit vectors for Cartesian systems. So to keep the matters general and discussion general, we are just using three unit vectors along coordinate directions. So the vector itself, as we know, has got you can express any vector in a given coordinate system using the three components that you can create of the vector along the coordinate directions. So you write it as a1 e1 plus a2 e3 cap, a2 it's wrongly written, e2 cap, and plus a3 e3 cap. So pardon this mistake, the second term is a2 e2 cap and not E3 cap. Okay, so A1 E1 plus A2 E2 cap plus A3 E3 cap. Now I would like to introduce the indicial notation with this. What is the indicial notation? The vector A, what I have written just now, can be just written using the summation convention, like AI, EI, and I is the summing index, and you can vary it from 1 to 3. So it means that the expression, when it is opened out using the summation operator, it will be the same what we have originally written down. Okay. Now here comes the real sort of concept behind the indicial notation. You know, in indicial notation, this was, by the way, first talked about and widely utilized by Albert Einstein. So we are actually now looking at how we can efficiently write vectors and tensors using this kind of a notation. Now, what is done in the next step? Actually, the summation is not written, but it doesn't mean that the summation is not there, right? Of course, summation has to be there. So, summation is implied over I. Now, I is recognized as a repeating index. What do you mean by repeating? As I've already shown here, A, I, E, I. So, what I have done here is, if you look at the bottom, there is a green both double-sided arrow that has been drawn from one eye to the other eye. So it means that in my expression that I have written on the right, A is equal to AI EI. In the expression you have I as a repeating index. Repeating means it occurs more than once. Okay, it could be occurring twice, it could be occurring thrice. So idea is if it occurs more than once, it's a repeating index in the expression. Okay, so in any indicial notation, you may have a repeating index, you may not have a repeating index. So if the index is repeating, then you have to sum over that index. That is the meaning when I say summation is implied. Okay, so that means any vector A is actually written without any summation, AI, EI. That's the idea. Then coming to tensor representation. So now since you have to deal, so the information of magnitude and direction is very clear. Magnitude is represented by AI and the direction by the unit vector EI cap. Now when you come to tensors, you have to now represent three informations, right? So here the magnitude is Tij and you have two unit vectors EI cap, EJ cap, just written without any operation in the middle. Okay, these unit vectors don't involve any dot, cross, which you are familiar, or addition. There's nothing in between. It's simply a pair of unit vectors EI cap, EJ cap. Why a pair? Because you have to have information of two directions in this quantity, which is tensor of rank 2. Now notice that there is repeating indices here. So I've already indicated by arrows at the bottom, green arrows. I is a repeating index and J is also a repeating index. So therefore I've written that summation is implied over both I and J. Okay, so it's a double summation, which you must imagine written before the expression Tij, E cap I, EJ cap. So we seem to be just omitting the summation with that summation actually present in our minds. Okay, that is what the idea is. Now you can see that if to further clarify that, if I were to really open this out, because there are two summations, so I will get when I open it out, it will look like this. It will have 9 sort of components in 3D if I open this out. So now to open it, the simple way is that you fix up I and you open J, and then you again change I and then again write all the J's, and then again change I and then write all the J's. So in 3D you have I and J varying from 1, 2 and 3. Okay, 3 coordinate directions. So that's why the first 3 terms have I fixed as 1 and J is varied from 1, 2 and 3. And likewise in the second, the I is fixed at 2 and J is again varied from 1, 2 and 3 and so on. Now so these are 9 components. So remember, a vector has 3 components in 3D, but a tensor of rank 2 will have 9 components in 3D. So it's actually much more complex than a vector. So these pairs of unit vectors, which are written just together to represent tensors, these are like what we have for vectors. We call them as simple unit vectors are there. Now since we have pairs of unit vectors, we have a special name for that. We call them as unit dyads. Okay, unit diodes. So E1, E1, E2, E1 cap, E1 cap, E1 cap, E2 cap, E1 cap, E3 cap. These are unit diodes necessary to represent tensors of rank 2 in any coordinate system. Right. Now we move on to the various algebra operations. So it's pretty straightforward: addition and subtraction. So addition subtraction requires both quantities to be either of the same type. So they have to be, both of them have to be either vectors, or both of them have to be tensors of rank 2. Unless the two quantities are of same type mathematically, they cannot be added or subtracted. Remember this. So that means if I have two vectors A plus B, I will write them as AI EI plus BI EI. So EI can be taken outside and AI plus BI. Notice that I is again a repeating index in this. So therefore remember to sum it. Okay. So the expression AI plus BI E cap I is actually having three terms, where I is summed from 1, 2 and 3. So you can see that the corresponding components of the two vectors are getting added. Same is the story with the tensors. So T1 tensor added to T2 tensor. So I will write it as Tij1 plus Tij2, and of course Ei cap, Ej cap, the diodes. So again here I and J are repeating indices. So you have a double summation, which is not written actually, but it is implied. So now we move on to the inner product, what we call as the dot product. See, more formal name in mathematics is inner and outer products for dot and cross products. But you are familiar with dot and cross products, so there's no harm in still calling it as a dot product. But we should also know a proper and more formal name in mathematics, which is the inner product. So when we deal with two vectors, see, inner product can be with two vectors, it can be with a vector and a tensor, and it can also be between two tensors. So we will discuss all of that, all these things. So the first thing that I am discussing with inner product is, suppose we want a dot product of two vectors. So we will write it as A dot B. And now since we are already knowing the indicial notation, so we will write the vectors as AI EI dot BJ EJ. Notice that once I use one index for representing one of the vectors, which is I for A, then I am using a different index J for the other vector. Now this is necessary because actually the two vectors are sum over I. For example, A has to be written as AI EI, implying sum over I. So I being a repeating index in that expression, and similarly B also needs a summation. Okay. So since I have already used up one of the indices for representing vector A, I must use a different index for representing the vector B. So that's why it is written as BJ EJ. Okay. I can't use I there because obviously then as per the summation convention, I will then not be doing correctly the dot product operation, as you will soon see later on as we follow. So so write the vectors or write the quantities with different indices. This is the key. So AI EI dot BJ EJ. Now if you expand it further, if you take it this thing further, then now you can simply since there is a dot product in between, and dot product applies to vectors only, so AI and BJ, which are just two real numbers or real quantities without any direction involved, so we can directly multiply them AI BJ and then write EI dot EJ, because after all the dot product must be applied to the unit vectors. So now notice again, whenever you arrive at some expression involving I and J or maybe even K, you must look at what are repeating indices and what are not. So here again with green arrow I have specifically indicated I is still a repeating index and j is also a repeating index. So you have to have a summation over both I and j. So for a general coordinate system, the dot product requires again sort of, if you open out the two summations I and j, then you will notice that you will again get 3 terms for each. So in all it gives me 3 into 3, 9 terms. So the dot product, you can see, for a general coordinate system will have 9 terms and not the usual 3 terms that you are familiar with, because you normally work with a Cartesian system, and which is an orthogonal coordinate system. So here is what you see, that a very general treatment for a general coordinate system which may not be orthogonal, the dot product looks like this: ai bj ei dot ej, summation over I and j implied. Now, but you notice also one thing, that the result comes out as a scalar. Why? Because after all, ai bj are just real numbers, and ei dot ej is also a scalar. So all the quantities written on the right for the dot product are just numbers. So the result will be just a scalar, not a vector. Okay, so the dot product comes out as a scalar, which is expected, and but for a general coordinate system will have 9 components. Now, as I told you earlier, we often use orthogonal coordinate systems. Now, orthogonal coordinate systems are one where the unit vectors are mutually perpendicular. So ei dot ej is 1 when we have I equal to j, meaning that e cap 1 dot e cap 1 is equal to e cap 2 dot e cap 2 and is equal to e cap 3 dot e cap 3, and all these dot products with themselves are going to be unity, because after all these are unit vectors. But ei dot ej will always be 0 whenever I is not equal to j. So this is because of the orthogonality of the coordinate system. e1 dot e2 is 0, e2 dot e3 is 0, and e1 dot e3 cap are 0. So the unit vector dot products are all 0 if I is not equal to j. So examples of orthogonal coordinate systems are Cartesian and cylindrical coordinate systems. Now, for orthogonal systems, the mathematics in mathematics we have a very elegant way of representing these unit vector dot products. So you must also be familiar, made familiar to this symbolic sort of elegance. So ei dot ej is given a special symbol in mathematics known as Kronecker delta, and which is written as delta ij. Okay, so for any orthogonal system, ei dot ej is written as delta ij, Kronecker delta. And what is the meaning? This symbol means that delta ij must be 1 when I is equal to j and must be 0 when I not equal to j. Of course, since this is being used to symbolically represent ei dot ej, it must have the same properties that the dot product of ei and ej cap, what properties they have. So delta ij has the same properties as the dot product of the unit vectors of a orthogonal coordinate system. So now what it does is it gives me some elegance in writing the dot product. A dot b is then simply written as ai bj delta ij. Now, since I am having indices on the Kronecker delta symbol, now I must say that I is a repeating index and j is also a repeating index. So if they are repeating indices, summation over I and j is again implied. So, but we know that delta will only contribute, or its value will only come as unity whenever j is equal to I. So otherwise it will be 0. So when you open out the two summations, summation over I and j, I can safely say that whenever j is equal to I, you will get a number or a contribution, otherwise it is 0. So therefore we can simply simplify this expression as ai bi. Why? Because I am simply replacing j by I, because whenever j is equal to I, delta I will be 1, right? And so therefore, instead of writing bj, I now write ai bi, and of course delta I would be 1. So it's not written explicitly there. So A dot B for orthogonal coordinate systems simply comes out as AI BI, and again I being a repeating index. Notice the very profound use of the fact that you have to be careful in monitoring the repeating indices, otherwise the whole indicial notation breaks down. So A dot B is equal to AI BI, and again I being a repeating index, so you have summation over I. So A dot B is equal to AI BI. Now this is a result which you are aware of, because you have been trained to deal with orthogonal coordinate systems only. So that's why this is a special case for orthogonal coordinate systems. So what we are essentially doing, the rule is multiply the corresponding components and add. So why add? Because I is a repeating index, so you have to add them. Now coming to the dot product involving a vector and a tensor of rank 2. So again A dot T, now we can move a little faster because we are now becoming familiar with indicial notation. So A dot T is equal to AI EI, this is the vector which is written using indicial notation, dot with again tensor written in indicial notation, tensor of rank 2. So notice again that since I have used up the I index, I have to write the tensor using some other index. So I am using j and k. So T, j, k, e, j, e, k. This is from the general representation what we have seen earlier. Then once these vectors and tensors are written, now you have to move ahead with the dot product. So as I said, AI and TJK, they are just magnitudes or real numbers, so they are just directly multiplied, AI, TJK. And notice here that since you have got pair of unit vectors EJ, EK, which are basically unit dyads, now notice that since EI is written on the left of this unit dyad EJ, EK, so the dot product is between EI and EJ and not EI and EK. This is important. Please, I am again repeating this. EI is a unit vector written on the left of the unit dyads EJ and EK. So when you take the dot product from the left side of EJ, EK, then the vector which is immediately neighboring the dot, that is involved in the dot product. So this is what it is. So EI will be involved in a dot product with EJ and not EK. So this is what is written below. Now you will notice here in this expression that again I am explicitly showing the repeating indices, because it's important to track them so that we can open out this expression correctly, because we need to know which index is involved in the summation. So I is repeating, J is repeating, and K is also repeating. So it means that I have to sum over three indices, I, J, and K. And this summation is implied. We are not explicitly writing. Now also notice that in this general expression that I have written for A dot T tensor, we will see that the right side involves a single vector EK cap. Okay. So since it involves a single unit vector EK cap, we immediately we can say that the result is a vector. Okay. So when we take a dot product of a vector and a tensor of rank 2, we don't get a scalar, but we get a vector. So notice this important conclusion. A dot T is actually a vector. Okay. So the result is a vector as it involves only EK. Now for vectors, we know that A dot B is same as B dot A, so it's commutative for vectors. But for vector and tensor, A dot T tensor is never equal to T dot A tensor. You can verify this using the dot product procedure and definition already discussed by me. So it's self verification exercise. That's why I've written do it yourself. And in general, it is not commutative. However, it will be commutative. A dot t is equal to t dot a only if t is, or the tensor, second rank tensor is symmetric. What is a symmetric tensor? Now I've written it below. Tij is equal to tji. That means the components behave in a manner such that Tij of the tensor components I am talking of, Tij is equal to Tji. So it's like T12 is equal to T21 and T13 is equal to T31, things like that. Remember, you must have learned this for stress tensor at a point in solid mechanics or even in fluid mechanics, that we have been told that stress tensor at a point is symmetric. This means that it qualifies as a symmetric tensor. So this result A dot T is equal to T dot A only if T is symmetric is important for fluid mechanics also. So remember these things. Now we move on to outer product, which we more commonly in common language we call as the cross product. Okay. Now I will go through this also quickly. Since you already know ideas related to cross product. So if you got two vectors A cross B, we write them as AI EI cap, BJ EJ cap, and involve the cross product in between. So again, we can write it as AI BJ and EI cross EJ. Again, we explicitly show you the repeating indices and summation over them is implied. So repeating indices are I and j, and therefore summation over I and j is implied. We also see that the result is a vector. Why? Because AI Bj are scalars and EI cross EJ is in general or behaves as a vector. Okay. So now let us look at orthogonal coordinate systems and things like that, how we can just simplify this for an orthogonal coordinate system. So if you look at a simple figure that I have shown a orthogonal general coordinate system. So E cap, E1 cap, E2 cap and E3 cap all are mutually orthogonal. So for an orthogonal right-handed system of unit vectors. Now what do we mean by right-handed? Right-handed means that we have this property that EI cross EJ is always equal to EK for cyclic combinations of I, J and K. Okay. So which I have further explicitly elaborated below. What is the meaning of right-hand system? The meaning is that as per the figure you can see that if you use the right-hand rule for which is normal. I'm sorry for ending the lecture at the previous slide. In fact, this is the last slide in the presentation. So I'm continuing my lecture onto this slide. Now in this slide I have shown some other types of products that we have involving vectors and tensors. So what are these? We call them as dyadic product of two vectors. Dyadic product of two vectors. Now you are already familiar with what is a unit dyad and all. So as you can see, the dyadic product of two general vectors A and B is simply written as two vectors A, B with no dot or cross or any operation symbol written in between them. So when you just write two vectors neighboring each other, you are basically writing a dyadic product which is written as AI, EI and of course BJ, EJ and then AI, BJ written together and the unit dyad EI cap, EJ cap written together. So as you can see, if you take two vectors and do a dyadic product, the result is a tensor of rank 2. Now in fluid mechanics, an example of such a dyadic product is the momentum flux at any point. It behaves as a tensor at a point. Now this momentum flux is written as a dyadic product of rho v and v. Okay. So rho is the density at a point, and v is of course the velocity vector at that point. So the momentum flux is sort of mass flow rate involved per unit area. So rho v. So the first vector is rho v and the other vector is v. So I've written dot product. I've written the dyadic product rather. Sorry for saying dot. It's not dot across. It's the dyadic product. There is no operator symbol between rho v and v. So it will be simply written as rho ui ei and uj ej, and then finally rho ui uj and ei cap ej cap, the unit diad. Okay. So this is the example from fluid mechanics of a dyadic product, the momentum flux tensor. Okay. Now we will look at tensor dot products. We have been discussing the dot and cross in the with the context of vectors. So let us use two tensors and see how we can define their dot products. So if there are two tensors P and Q in general, so I write them as Pij ei cap ej cap and Qrs er cap es cap. Notice again that since I have used ij in representing P tensor, I am using different indices R and S for Q. So now the dot product is simply written as P tensor dot Q tensor. This is equal to Pij ei ej, and on the other side I write Qrs eres. Now the unit vectors involved in the dot product from P side and from Q side are the ones which are immediately adjoining the dot operator. So that means if the dot operator is in the middle, then the second unit vector ej cap from P will be involved in the dot product with the first unit vector in tensor Q. So I repeat, in this kind of dot product, the second unit vector from the first tensor will be involved in the dot product with first unit vector of the second tensor. Okay, so that's why it's written as Pij ei ej dot er Qrs es, and then Pij Qrs scale normal real numbers, so they are just taken together, Pij Qrs. And EIES, remember EI is always to be written towards the left of ES, okay, otherwise the meaning changes. So EIES and EJ dot ER is again scalar entity, so no need to bother with that a great deal in terms of direction and all. So the result is, as you can see, P dot Q has a unit dyad involved, ei cap es cap, so it will be a tensor of rank 2. Result is a tensor of rank 2, and notice that I, J, R and S all are repeating indices, so summation over all four of them is implied for a general coordinate system. Now for orthogonal coordinate systems, Ej dot Er will be replaced by Kronecker delta Jr, okay, delta Jr. So in the next step for orthogonal systems, we have this expression, and then if you want to just open out the summation using the fact that Kronecker delta only contributes whenever R is equal to J, otherwise it is 0. So therefore you simply replace R by J and remove delta JR from the expression. So Pij Q, R is replaced by J, QJS, and delta JJ is then 1, so EIES. So now you have a simplified expression which gives you repeating indices I, J and S, so summation over I, J and S. So for orthogonal systems, you have a simplified result in terms of summation is only over 3 indices. The result is still a tensor of rank 2, of course. This is a general result. If you involve two rank 2 tensors and take a dot product, then the result is again a tensor of rank 2. Finally, to conclude this lecture, a double dot product is also defined for two tensors of rank 2 as. So this is a totally new idea, double dot product. So it's written as P tensor, then like a colon, you write two dots, one over the other, and Q tensor. So this, in this case, you involve all the 4 unit vectors, from 2 from P and 2 from QRS. You involve both of them in a dot product. So how they are involved? The inner ones, the second from P and the first from Q, is involved in a dot product, EJ.ER, and the other two, that is the first from P and last from Q, they are also involved in the dot product. So Pij QRS and EJ.ER, the second from first and then first from second, and the other dot product is between the remaining two unit vectors, EI and ES. So you've got two dot products involved. So final result comes out as a scalar. There is no vector here in this expression. So notice that a double dot product involving tensors of rank 2 results in a scalar. Okay. So tensors can be reduced into scalars by involving a double dot product. So again, for orthogonal systems, you can replace these dot products of unit vectors by the canonical delta symbols, delta JR and delta IS, and then again for R is equal to J and for S is equal to I, you can just simplify them by simply replacing S by I and R by J. Otherwise the canonical delta just gives 0. So therefore the summation finally remains over I and J, and the expression for orthogonal systems is that the double dot product of two tensors P and Q for orthogonal systems is simply Pij Qji. Okay, Pij Qji. So again we have repeating indices I and J, so you need to sum over both I and J. So with this we finally conclude this lecture. Pardon me for concluding it prematurely on the last slide. Remember to watch this slide concerning tensor dot products and dyadic products of two vectors also. Thank you very much.